In this final clip of the ENFUSE module on power measurement, we bring some systems thinking or big picture context to the material presented. We do this by considering 7 key aspects related to systems thinking and engineering design. The first aspect pertains to the mission or overall goals that influence the design. In this module, our objective was to consider methods for measuring power. We looked at inline approaches and conducted an experiment using a non-invasive measurement method. Recall that the inline method put an ammeter in series with the load. So here's our load, and then we had an ammeter in series. And then in addition, we put a voltmeter in parallel to the load. All right. So this was relatively invasive. We have to break the line going to the load to put the ammeter in series. And also we have to be able to tap into the conductors to measure the voltage across the load. So that's our invasive or direct method. We also looked at an indirect method, right, where the current through the load was inferred through a split coil transformer that had current induced in it. And then we measured the voltage across a very small resistor. And then the relationship between that current in the coil and the current in the main line was dependent on the number of turns in the transformer. Okay. So the second aspect we have here pertains to system-centric constraints. Of this list here, the one that should jump out would be the one pertaining to safety. Right? Our non-invasive method allows you to readily determine the power use of a variety of household devices without any exposure to uninsulated wiring. We might also think about opportunities related to society and the environment, right, if one's knowledge of power use were better understood. In regards to performance metrics, the third aspect, our homemade current sensor won't have the accuracy of the purchase sensor unless one spends a good deal of time with calibration and has better controls in terms of its production. But it is also less expensive. So we might have that accuracy goes up with the amount of money you're willing to spend on it. Likewise, our purchase sensor was less expensive than the power meter on your house, but I don't think anyone would prefer its measurement for billing purposes. We looked at a few different models in terms of direct power measurements and used them to glean that large internal resistance is requisite in a voltmeter and very small internal resistance is needed in an ammeter. So if we recall, if this is our load and we have a voltmeter in parallel, then by current division we want very little current flowing through here and the majority of current flowing through here so that the voltmeter doesn't influence the overall performance of the system, in which case we need a very large internal resistance in the voltmeter. In contrast, if we have an ammeter in series with the load, right, then we want very little voltage drop across the ammeter, which means it needs very small internal resistance. We didn't discuss layering per se, the fourth aspect, but one can extend the idea of measuring power at a particular appliance to the power measured at a house, neighborhood, etc. Utilities have a good sense of the power at these upper layers, especially with the advent of smart metering or AMIs, but it's within the household that there are new opportunities for making use of these measurements to reduce peak loads. Following up with the previous aspect regarding layers, it's clear that one layer's power will be the aggregate of power at lower layers. For example, let's consider a neighborhood, and the power of a neighborhood is the aggregate of the power of the homes in the neighborhood, street lighting, etc. To take this to the extreme, the power used by an appliance, the lowest layer that we considered in our experiment, is the aggregate of the power used by its subcomponents. Consider a refrigerator, whose power is primarily based on its compressor motor, but might also require power for any embedded control system, its lighting, ice making apparatus, etc. So we could replace this diagram with R for the neighborhood, right? That's our refrigerator, and then each one of these would be subsystems within the refrigerator. So the diagram is very similar, it's just at a different scale. The sixth aspect relates to flow of power and information. If you recall from our introduction, this aspect clearly ties to the smart grid that we described as simply an overlay of an information network on the existing power network. Thus the intent is that wherever power flows, the information will flow. Information might only flow between two layers, such as will occur in a smart home energy management system, right? So here is one layer that might have a controller and that works in concert with the AMI, and then at the lower layer could be all your smart appliances, right? And power and information, well, information is flowing between them, and power would be flowing to the appliances, right? Or information may flow across many layers, as might be the case should there be centralized control of electric vehicle charging to avoid overloading the power system infrastructure. Finally, in terms of design trade-offs, we can again look at the accuracy of using a non-invasive method for measuring power, with the safety concerns of doing a direct power measurement using an inline current meter. We hope that for whatever problem you are working on, you will revisit these 7 system thinking aspects. Understanding how systems interrelate and how they impact societal concerns is not an easy thing to learn, and it's certainly different than studying equations that you probably have done in your courses to date. But being aware of these aspects is a very good first step, and one that will make you a better engineer.